right, so in 1.7 we're going to talk about selecting procedures for choosing limits. This is sort of just a general, I'm going to toss some limit problems at you and show you some different techniques, some tricks to look out for as you solve these expressions. So let's jump in. A couple things that you need to know first. There are a couple trig identities that you will have to have memorized for AP Calculus, namely the ones on the left, the Pythagorean identities. And so I can real quick give you kind of a brief overview about where these come from. So if we think of our unit circle, it's just our circle that has a radius of 1. It's going to have an x component and a y component. We can think of that point being the point xy, right? And so the way we develop our unit circle is we recognize, okay, well, that radius makes some angle theta with the x-axis. And notice that sine of theta being opposite over hypotenuse, well, that would be y over 1, which is just y. So that y value actually corresponds to sine of the angle between the radius and the x-axis. Likewise, the x value will correspond to cosine of that angle. And so now that we know that x equals cosine theta and y equals sine theta, and those are components of this right triangle that we have here, well, what do we know about right triangles? Their sides satisfy the Pythagorean theorem, right? So therefore x squared plus y squared equals 1 squared, which is just 1. And I know that x is cosine theta, so I can say cosine squared theta plus sine squared theta is also 1, just by substitution. And so that's where our basic, that first Pythagorean identity at the top comes from. Once you have that one memorized, you can develop the other two. So all we need to do to develop the other two is to divide. So if I divide everything by sine squared theta, well, 1 over sine squared is cosecant squared. And sine over sine is 1. And cosine squared over sine squared is cotangent squared. So that gets me that third one. Whereas if I instead divided everything by cosine squared, I would end up with, on the right-hand side, 1 over cosine squared is secant squared. So you end up with that middle Pythagorean identity. The others you don't technically have to have memorized for the AP exam, although they come up a little bit, so it's helpful. But I just wanted to give you those trig identities because we will be using them in some of the examples today. All right, so let's start out with this first one. Now that we're kind of fully into dealing with limits, when you're trying to evaluate a limit, the first thing I generally try is a direct substitution. If you can do a direct substitution and it comes out to a value, that's your answer. So let's do a little review of how to actually utilize the unit circle. So in a case like this, we would know, okay, pi over 2 is up there. Here's my unit circle. That coordinate on the unit circle would be the coordinate 0, 1. And so then I could recognize, oh, okay, so sine of pi over 2 is 1 and cosine of pi over 2 is 0. And that'll let me, or help me to evaluate this. So I know that cosine of pi over 2 is 0, so I have 3 times 0 over 2 minus 2 times sine of pi over 2 is 1. So we end up with 0 over 0. And I want to remind you that that's not necessarily undefined or that the limit does not exist. This is an indeterminate form. So what we need to do is try and maybe use algebra or trig identities to rewrite our limiting function to see if we can write it in a new way that does allow us to make a direct substitution. So let's try that. And I got those trig identities. I'm going to use my first Pythagorean identity to replace that. So that first Pythagorean identity, remember, is sine squared theta plus cosine squared theta equals 1. Well, therefore, I can isolate cosine squared and say, oh, cosine squared theta is 1 minus sine squared theta, right? All right, so now I can make a replacement in that numerator. Don't drop your limit notation here. So we're still approaching pi over 2. We're just doing a substitution for cosine squared, and we're replacing it with 1 minus sine squared x in this case. And that's over 2 minus 2 sine x. All right, I'm still going to end up with 0 over 0 at this point if I do a direct substitution. I haven't canceled anything or anything like that. So we have kind of a few more steps. The other thing that I want to remember that comes in handy quite a bit is my difference of squares, right? Difference of squares factors to a plus b, a minus b. So down here I do have a difference of squares. Namely here. 1 is a perfect square and sine squared is a perfect square. So that becomes 3 times 1 minus sine times 1 plus sine. In the denominator, I can factor out a 2, so I'll have 2 times 1 minus sine. And now I can actually cancel something. So I have 2 factors of 1 minus sine. Let's get rid of that. Look at my limit now as x approaches pi over 2 of 3 times 1 plus sine over 2. All right, so now let's see if we can actually evaluate this through direct substitution. Once you make the substitution, that's when you get to drop that limit notation. So 3 times 1 plus sine pi over 2 over 2. So we look back up to our unit circle. Sine of pi over 2 is 1. So I have 3 times the quantity 1 plus 1 over 2, which is, what, 6 over 2. And my answer is 3. All right, let's move on to the next example. In this case, find the limit as x approaches 3 of 2x plus the absolute value of x minus 3. Again, here I'm just trying a direct substitution. If it works and gets me a value, great. 2 times 3 plus absolute value of 3 minus 3, which is 6 plus 0, which is 6. Great, that's it. Nothing tricky about that one. I just wanted to throw absolute value in there. Kind of wanted to show you what that graph looks like. So if we look at, whoops, (2x) plus the absolute value of x minus 3. Oops. You can see there is a little kink in that graph. There's a little corner right there, but the limit's still approaching the same thing from the left and the right. So that limit is still going to be 6, just as we found algebraically. We will come to find in a little bit in the next unit that there is an issue with the calculus at that little kind of kink in the curve. But we'll approach that in the next unit. All right. What about something like this? We're looking at the limit of 2x plus 12 over the absolute value of x plus 6 as x approaches negative 6. So in this case, if we do our direct substitution, we're going to get negative 12 plus 12 over 0. We got 0 over 0. So that's our indeterminate form. All right. So let's make note here that our denominator does seem to be approaching 0, and we have an absolute value here. So here's how we're going to have to take care of that. What we want to look at is what's going on as we approach -6 from either side. So from the left versus from the right. Let's look from the right first. So what we mean by that, right, is that we're approaching -6, but from larger values than -6. So that's like -5.9, -5.99, -5.999, and so on. So here, if I were to plug in -5.9 for x, nope, not -0.59, -5.9, and add that to 6, I'm going to get positive 0.1, and I'm going to have the absolute value around that, which is going to return just 0.1, right? And if I plug in -0.99, I'm going to get positive 0.01. Take the absolute value of that, that's going to return just 0.01. So my point is, as long as we're approaching -6 from the right, the absolute value isn't doing anything. My value within the absolute value is already positive, so the absolute value just returns whatever x plus 6 is. So if I want to look at it from the right, I can just drop the absolute value bars altogether because they aren't changing anything. So when I do that, what I have is 2x plus 12 over x plus 6. So let's simplify that, because we know if we just do a direct substitution, we get that indeterminate form of 0 over 0. So we can factor out a 2. We'd have 2 times x plus 6 over x plus 6. I can then go, aha, common factors, I can get rid of it. Now I'm just looking at the limit as x approaches -6 from the right of 2. The limit of a constant is that constant. So from the right, as x approaches -6, we are approaching 2. Sorry, I just saw my bad notation over here. Let me correct that. X, there we go, approaches -6. All right, now let's talk about what's going on from the left. So as x approaches -6 from the left, well, now if I plug in values of x that are approaching -6 but to the left of -6, that's like -6.1. So notice if I were to plug that in for x, I would have absolute value of -0.1, and now the absolute value is doing some heavy lifting. It's going to take off that negative, and it's going to return positive 0.1, right? So here's the deal. When I evaluate it from the right, I can drop the absolute value again, but what I need to recognize is that the denominator will return the opposite of x plus 6. So we can express opposite of just using negative. Negative just makes it the opposite, right? And now I can try simplifying again. So again, let's factor out, whoops, get back to my blue. Let's factor out the 2 in the numerator. X plus 6 over negative, I'm just going to call it -1 times x plus 6. Still have that common factor. But now I'm going to have 2 over -1, which just simplifies to -2. And still the limit of a constant is a constant. But now notice my right-hand limits and left-hand limits do not approach the same thing. Therefore, our final answer is that the limit does not exist. All right, let's move on to the next example. Okay, here's another one with trig. Still, try direct substitution. If that gets you a value, that's your answer. If not, then we'll have to try something else. So, if I do a direct substitution, we're going to end up with 1 plus √2 sine of -pi over 4. Oh, what did I write there? Root sine? I meant √2. Over cosine of 2 times negative pi over 4. Okay, so let's see. 1 plus root 2 times sine of negative pi over 4 over cosine of negative pi over 2. We're going to look back at our unit circle one more time here. All right, so negative angles are always in the clockwise direction, so negative pi over 4 is going to make a triangle down here. And that's a 45, 45, 90 degree triangle, so it's going to be 1, 1, rad 2. So this one is negative because it's the y component, and we're below the x-axis. So if we want sine of that angle, sine is opposite over hypotenuse, so it's going to be negative 1 over root 2. All right, so let's see. 1 plus root 2 times negative 1 over root 2. I'll simplify that in a moment. Cosine of negative pi over 2. This angle is negative pi over 2. It's a quadrantal angle, so we can just think of what would the coordinates there be? So that would be the coordinate 0, negative 1. Cosine is the x-coordinate, so 0. Get over 0. That cancels. And we have our indeterminate form once again. So that means we have to try and simplify algebraically, then retry our direct substitution. All right. Well, what can we do? I noticed that the denominator is cosine 2 theta, and at the beginning I gave you a few identities for cosine 2 theta. There's 3 of them, so it might be tricky to figure out which one to use. But remember, to be able to do a direct substitution and get something other than the 0 over 0 that we originally got, you're going to have to cancel out factors. So, with that in mind, if we can take a look at what's in our numerator, 1 plus root 2 sine theta. I know I'm going to have to cancel something to do with sine. I probably don't want a cosine in my numerator. The only one of these identities that involves only sine is the 1 minus 2 sine squared theta. So let's go with that. All right, so we're going to rewrite our limit. So here we go, limit theta approaching negative pi over 4. My numerator is 1 plus root 2 sine theta. My denominator, now I'm replacing cosine 2 theta with 1 minus 2 sine squared theta. And that just comes from that identity on the first slide. All right, well, I can't cancel anything yet. I need to try and factor things. And once again, it's going to be our difference of squares that comes in so handy. So a squared minus b squared factors to a plus b, a minus b. In this case, we're going to consider a to be 1. This whole thing is b, 2 sine squared theta. And that's going to mean that if we follow that pattern, my numerator is still 1 plus root 2 sine theta. My denominator is going to be 1 plus root 2 sine theta times 1 minus root 2 sine theta. And now I have common factors of 1 plus root 2 sine theta in my numerator. We're off to the races. So limit theta approaches negative pi over 4 of 1 over 1 minus root 2 sine theta. Whoops, getting ahead of myself. There we go. Now we're ready to do the direct substitution, and that's the only time that it's okay to drop your limit notation. So sine of negative pi over 4, which we already found out is negative 1 over root 2. So I have 1 over 1 minus root 2 times negative 1 over root 2. These two are going to cancel each other out. Negative times negative makes a positive. So this becomes 1 over 1 plus 1, which is 1/2. All right, great. That one took a little doing, but it's a good example to go through just so you can see kind of some of the tricks. All right, so here's your first student example. Give that one a try. You can just pause it here, copy it down, get an answer, and we'll go over it in class. And then I got one more student example. This one's multiple choice, so give this one a try. Pause it here, choose an answer, and we will go over it in class. I'll also upload the slides themselves so you can have those to reference if you need. All right, see you in class.